Before we dive into the concept of coroutines, let's start with a comparison by looking at a standard C# methods. This will help us highlight the key differences. Let's imagine a scenario where we need to fade an object out by changing its alpha value. We'll start by creating a new C# script named *fade. First, let's tidy up the file and, crucially, import the Unity engine.ui namespace. Next, we need a reference to our object, so let's add a public image variable named myImage, along with a custom method called changeAlpha. Inside, we'll cache the current color of the image into a temporary variable called newColor. To achieve a fading effect, we need to modify the alpha channel gradually. We'll use a for loop for this. We initialize I at 1, and as long as it's greater than 0, we decrement it by 0.2 in every cycle. We then apply this I value to our color's alpha and assign the result back to the image. Now, we need a way to fire this logic. Let's trigger the changeAlpha method inside start. I'll just adjust the syntax highlighting here for better readability. Let's save this and jump into the editor to test. Let's create a game object called logic and attach our new script. We'll drag our star image into the exposed slot. Now, watch closely. When we hit play, the image vanishes instantly. This isn't the smooth fade we wanted. Let's fix that. A common workaround is to move this logic into the update loop. We'll set up the same logic, checking if the alpha is greater than 0, subtracting 0.2, and applying the color. Let's comment out the old method in start, save, and see what happens. Back in Unity, we press play. It works. We have a gradual fade. However, this approach is messy. We are now constantly running checks in our update loop every single frame, even after the fade is finished. This is where coroutines come in to save the day. To define a coroutine, we use the return type IEnumerator and name it changeAlphaRoutine. In the body, we can essentially copy-paste our original logic. However, there is one critical addition. Inside the loop, we add yield_return_null. This line is the magic switch. It tells Unity to pause this specific function right here, render the current frame, and then pick up exactly where it left off in the next frame. Because this is inside our loop, the code effectively waits for a frame between every alpha change, creating that smooth animation we want. To run this, we use the specific method startCoroutine and pass in our routine's name. We can now disable that messy update loop entirely. Let's save and test. As you can see, the result is visually identical to the update loop, but under the hood, it's much cleaner. We aren't wasting resources checking conditions every frame, and the logic is self-contained. Let's refine this further. Previously, we only yielded inside the loop, but we can also control exactly when the coroutine begins. Let's add yield return new WaitForEndOfFrame at the very top of the function before the loop starts. By waiting for the end of the frame, we ensure the render cycle is complete before we modify the visuals, resulting in a buttery smooth start. Let's verify. And there it is, zero choppiness. So, to recap, what exactly is a coroutine? Think of it as a method that can pause and resume execution over time. They allow for reusable modular code. You can pause, stop, or resume them whenever you like. They are perfect for spreading heavy tasks across multiple frames to optimize performance. Just a quick heads up, this video is actually part of a complete course. If you're finding this helpful and want the full experience, you have 3 options. You can buy it directly from my Patreon shop or pick it up on Udemy. But for the ultimate value, check out my legendary tier on Patreon. That unlocks access to every course I've ever made, plus all my Unity assets links are in the description. Now let's move beyond the basics and explore the specific tools Unity provides to control this timing. While we've established that every coroutine needs a yield return statement to function, we aren't limited to just returning null. Unity grants us significantly more power through the yield instruction class. These are specialized, predefined instructions that tell our coroutine exactly when to wake up based on specific internal conditions. Let's look at the available options. WaitForSeconds. This suspends execution for a specific duration based on scale time. This is important because it means the wait time will be affected by time.timescale variable, so it pauses if your game is paused. WaitForSecondsRealtime. Unlike the previous example, this tracks the actual clock time, completely ignoring the time.timescale variable, making it perfect for UI animations or menus that work even when the game is paused. WaitForFixedUpdate. This synchronizes our coroutine with the physics engine, pausing it until the next fixed update cycle runs. WaitForEndOfFrame. This waits until the entire frame rendering pipeline is finished, after all cameras and UI elements are drawn, but right before the image is displayed on the screen. Wait until. For logic-based pauses, this suspends execution until a specific condition, supplied via a delegate, returns true. Wait while. This functions identically to wait until, except it keeps the coroutine paused as long as the condition remains true, resuming only when it returns false. Async operation. We can also yield an async operation. This is standard for loading tasks, such as waiting for a new scene to finish loading asynchronously. IEnumerator. Another powerful technique is to yield return a nested IEnumerator. This effectively pauses the current coroutine until another coroutine finishes its job. This is incredibly useful for creating sequences where you want a list of actions to happen one after the other. Custom yield instruction. Finally, we have a special case. By extending the custom yield instruction class, we can write our own unique logic to control exactly when a coroutine should suspend or resume. Now that we have a solid grasp of the different yield instructions available to us, we need to address the next logical step: lifecycle management. Specifically, we are going to master the different ways to start and, more importantly, stop these coroutines effectively. Let's dive in. First, let's create a new C# script and name it start-stop. Open the script and clear the default code. We need to access UI elements, so import the Unity Engine UI namespace, add a public image variable called myImage. Now let's define our logic using an IEnumerator named changeFill. We want to animate the fill amount over time, initialize a float elapsed time to 0, create a while loop that runs as long as elapsed time is less than or equal to 1. Inside, we increment elapsed time by time delta time. Since this value stays between 0 and 1, we can assign it directly to myImage.fillAmount. Crucially, remember to add yield return null to ensure the loop waits for the next frame before continuing. Now let's create a public run method. We'll call start coroutine and pass our function call directly as the parameter. We also need a public stop method. Logically, we try calling stop coroutine passing the same function parameter. Let's add some debug logs to both methods so we can track exactly when they trigger. Save the script and let's return to the editor. Create a new game object named startStop and attach our new script. Expand the start buttons prefab and drag the star image into the myImage slot. Now for the buttons, select button play, add a new onClick event and link the startStop object. Select the run function. Do the same for button stop, linking it to the stop function. Let's hit play. You'll notice clicking the buttons does nothing. This is because our prefab is a canvas, but our scene lacks an event system. Right-click in the hierarchy, go to UI and select Event System to fix this. Let's test again. Hitting play starts the animation and logs the message. However, when we click stop, the console says stop, but the animation keeps running. Let's look at the script. Start coroutine works fine with a direct function call, but stop coroutine cannot stop a routine started this way because it doesn't know which instance of the function you are referring to. Let's try a different approach. Strings. Replace the function parameters with the string name changeFill in both the start and stop methods. Save and test. Back in the scene, press play, then stop. It works perfectly. However, relying on strings is brittle. If you change the method name later, this code breaks without warning. Let me show you the preferred robust method. We need to store a reference to the specific coroutine instance. Define a private IEnumerator variable named myRoutine. Inside the run method, we assign the specific changeFill call to this myRoutine variable. We then pass this variable into start coroutine. For the stop method, we first check if myRoutine is not null. If it exists, we pass that specific variable to stop coroutine, save and test. Run the scene. Play starts it, stop ends it. It works just as well as the string method, but is type safe and cleaner. We have one edge case left. If you click play multiple times rapidly, multiple coroutines start running on top of each other, making the fill speed erratic. Let's fix this in the script. To prevent the coroutine from running multiple times simultaneously, we simply need to execute our stop logic immediately before starting the new one. We can also remove the debug logs now, save and do a final test. Now even if you spam the play button, it resets cleanly every time and stop works instantly. And there you have it, a robust system for managing coroutines. If you found this deep dive into coroutines helpful, please hit that like button and consider subscribing to the channel for more Unity tutorials. Thanks for watching, and I'll see you in the next video.